So in this video, we're going to look at matter a little bit more closely and think about what maybe it's made of and how the properties of different states of matter might be explained by thinking about what matter is made of and how what it's made of is arranged. So we're going to be thinking about particles. But just before we do that, I just want you to remind yourself about some of the properties of solids and liquids and gases that we did in the previous video. And it'd be great if you could have a think about which state or states you believe out of those three can flow. So make a decision, make an answer. And then also which state can change its volume. So try and recall those properties. Try and recall which states of matter have those properties. Okay, so we're going to be thinking about how we can explain these properties now. I'm not going to answer those questions just yet because hopefully they'll become clear as we go through the rest of this video. So one thing is that all material made up of tiny particles, that's going to be key now to how we're looking at and explaining those properties. And it's not just the fact that they're made of tiny particles, because of course if it's a solid or it's a liquid or it's a gas, it's still made of those particles. So it's also going to be regarding how they're arranged. That means how they're sort of put together or stuck together. It's going to be regarding their movement. And those two properties in particular, or two aspects are going to help explain the different properties of solids, liquids and gases. So this is called the particle model. So it's a model that we've got of how things are. So it states the following, right? So it's saying that it doesn't matter which state we're talking about, whether it's a solid, a liquid or a gas, they're all made up of very, very small particles. They are so small that it is just impossible to see them. You can never see them with the naked eye. And in fact, they're so small you couldn't see them with a light microscope either. They're always moving. That's very important. And we're going to consider how they move. And they always have spaces between them. Now, to say they have spaces between them is not to say that these spaces are necessarily big. So we're going to have to consider about the size of these spaces between the particles. And then finally, particles are held together by forces of attraction, sort of stickiness, if you want to think of it that way. But it's good to get into the habit of using this term, forces of attraction. So here we've got sort of a visual representation of what a solid might look like in terms of its particles. So what can we say about this? It's clear that they're moving, right? You can see that their particles are moving, but they're not moving around the box. They are basically staying where they are. What they're doing is they're vibrating. So they're vibrating about a fixed position. That is the way that we would describe the sort of motion of those particles in a solid. So they are vibrating, they're sort of jiggling from side to side, up and down and so on. They are jiggling, they're vibrating, but they are doing so in a fixed point. It's a little bit like you just standing on the spot, but sort of swaying from side to side. The other thing about them is that there is a sort of a nice, neat arrangement. We would describe this being a regular arrangement. We could imagine how that box continued, or how more particles would continue, what the shape would be like. So we call it a regular arrangement, and we also call it a repeating arrangement. So we can describe this as a regular and repeating arrangement of particles. So the other thing to say about them is those particles are very close together, right? So we say they're packed very close. So there are little spaces, but that the spaces between the particles is very, very small. So we would describe solids as being dense. What that means is all the matter that makes up a solid is all sort of in practically as small a space as it possibly could be. The particles are essentially as close as they can possibly be together. You've packed them as densely as you can. And then the other thing about them is that the forces of attraction, we said that in the particle model there were always forces of attraction. Well, it's because of those forces of attraction, it's because they are so strong that these particles are only able to vibrate around fixed positions, which is what they're doing. So in a sense, what we've got written there is the core or the key part of what we mean to say, or how we describe solids when using the particle model. It also helps explain properties. If we think about, when you think back about which state or states you said could flow, I'm hoping that you didn't say solids could flow, because they can't. They keep their shape, and for something to flow, its shape needs to be flexible, I guess. And because they're so close together, you can't compress solids. By compressing, what we mean is squashing into a smaller volume. So we couldn't make those particles really take up any smaller space. We couldn't squeeze that box and make it a smaller box and still have the same number of particles. There's very little space between the particles, and there's nowhere else for them to go. So we couldn't be squashed into a smaller volume. We've talked about the forces of attraction. We said in a solid that they are strong, but to get an idea of how strong they are, really we have to think about the melting points, and when it's a liquid, the boiling point. So if we just consider two metals, so these are both solid at room temperature. So if we had some calcium in front of us, it would be a solid, and if we had some iron in front of us, it would also be a solid. And we can see we've got here the two melting points. So calcium has a melting point of 842 degrees Celsius. That's very, very hot. But iron has a melting point that's almost twice as large. So we would have to heat up iron by significantly more. We'd have to heat up iron significantly more to melt it when compared with calcium. What that tells us is that even though the forces of attraction are strong in both of them, the forces of attraction must be stronger in iron because it requires more energy, and temperature is really a reflection of energy. It requires more energy to melt the iron to overcome those forces of attraction. That's sort of, I appreciate this language is quite unusual, maybe sounding, and I'm really just introducing it now. But if you are wanting to unstick something, you have to sort of be able to pull them apart, and that requires you to put a bit of effort in, that requires energy. And what we're saying is to unstick the particles in iron requires a lot more energy than it does to unstick them in calcium. But instead of unsticking, we're going to use the term overcoming the forces of attraction. So just repeating really what I just said there. So here we got a liquid. So you can see this is quite different to the solid. So for a start, it's taking up the shape of the container, but it's doing it so from the bottom upwards. So if you think about, if you had a half-drunk bottle of water, you know that the water would be sat in the bottom half of the bottle. If you then poured it into a cup, it would take the shape of the bottom part of the cup. You can see that the particles are moving faster than they were in the solid model, and also they are moving around. Okay, they're no longer in a fixed position. They're no longer vibrating. They're actually moving. However, they may be moving, but they are still closely packed. There's still not a lot of space where the actual particles are, or between the actual particles. So that's something important to consider there. So they're still very close together, just like they were in the solid, but because the particles are now basically free to move around each other, that must mean that the forces of attraction are weaker than they were in a solid. And yeah, they're always moving. Those particles are changing places all the time. Because the particles are allowed free to move, that is the reason why liquids can actually flow easily, and that's why they take the shape of the container they're in. Solids weren't able to do that. So this is a property that a liquid has, the ability to flow, that solids don't have. There's still, like I said, little space between the particles. So again, just like with solids, you can't squeeze a liquid into a smaller space. The word we use to describe whether something's being squeezed or not into a smaller space is compressed. So if we say something can be compressed, we're saying it can be squeezed to take up a smaller space or a smaller volume. Liquids can't be compressed. Solids can't be compressed either. When we look at gases, I'm hoping the first thing you notice is how much space there is between the particles. Sure, sometimes they get very close to each other, but generally speaking, when you think about the area that you've got in the box, there's way more space than there is particles. They're moving around very freely. They are taking up the entire space, so they're not just at the bottom like liquids were. So they're constantly moving. They can hit each other. There's a lot of space between them. So this is going to explain, you can now get an idea from the particles here, how they're arranged, their movement, etc., how we can explain some of the properties of gases. So yeah, there's that space. So this is just a description of what I've just said. There's that space, they bounce around, sometimes they hit each other, but generally speaking they're far apart. This explains why gases can flow as well, and also explains why they can spread out to fill any available space. So when you're in a room, the entire room has got air in it. It's not just at the bottom, it's not just at the side, it's not, wherever. The air particles are throughout the room, completely spread out throughout the room, so they would take up any available space. Gas, though, this means that gas, and you look at that, you look at the box at the bottom there, and you look at the particles in it, it's mostly empty space. Now, empty space means nothing, okay? But we are talking at a very, very small scale here. Now, what we could do is we could compress this gas. If we squeezed, we sort of pushed in the side walls and we pushed in the top walls, we would be able to make those particles take up a much smaller space, a much smaller volume. So this is something that absolutely distinguishes gases from solids and liquids. The fact that they can be compressed. There is a lot of space between the particles, and we can take advantage of that to squeeze the particles into a smaller space. And that's why it's possible to change the volume of a gas. So this is a sort of a summary. It's a nice, lovely, neat table. So if we just focus at the top, so we've got our regular repeating pattern in our solid particle model here. If I asked you to add more particles, you would have a very clear idea of where you could add them. They are not taking the shape of the container, so they have their own shape, right? Solids have their own particular shape, and that doesn't change just because you put it in a particular container. If we look at the liquid, we can see that there's a random arrangement of the particles. They are like solids, there is very little space between the particles. Here they are taking up the shape of the container. You can imagine this as being a little bit like having a jar of marbles. So the marbles could move around, you could shake them and so on, but they would sit at the bottom and they take up the shape of whatever the jar is. And then gas, we've got them all spread out, taking up the full shape of the container, and they would be absolutely constantly moving. So in our solid they would be vibrating from about a fixed point. In our liquid they would be constantly moving around each other, changing places, and in a gas they would just be moving around the entire volume of the container. So I've just mentioned some of the things in the volume, shape and density just then. So these are just different ways of describing that. If we were talking about the energy of the particles, and we'll understand this a little better on the next video when we look at the particle model and changes of state, we would describe the energy of the particles in the solid as being low, in a liquid as being medium, and in a gas as being high. We're just making this comparison between each other. What we're saying is the energy of the particles in a liquid of a substance, liquid state of a substance, is greater than the energy of the particles in the solid of the same substance, and then the energy of the same particles in the gas form of the substance would be highest. The compression, this is all about the spaces between the particles. So there is very little space, so you can't compress the particles in a solid, or you can't compress solids. You can't compress liquids for the same reason, but you can compress gases because there is a lot of space between the particles. Forces of attraction, very strong in a solid, strong in a liquid, and weak in a gas. And then the question of whether they can flow. Solids can't, but liquids and gases can. So just to finish this video, just going to have some true or false questions. I just want you to basically maybe pause the video, look at these questions, write true or false, depending on which you think is the case for each of them, and then I'm going to reveal them in a second. So pause the video and then have a look at the answers. So the first one, false, right? Because there is nothing between the particles, absolutely nothing. In fact, if we're talking about air, we're talking about air particles. So you can't have air particles between air particles, as it were. I mean, you can't have them being the space in between. So there is nothing between the particles in a gas. Liquids and gases do take the shape of their container. The reason for that is because the particles are free to move around, and there are weaker forces, certainly compared to solids. It's not because the particles are very hard that solids and liquids can't be squashed. It's because there's very little space between those particles. Okay, so we don't know exactly how much further apart gas particles are, but we know they're a lot further apart than those in a liquid or a solid. So whilst you might not know it's 1,000 times, and maybe it's not always 1,000 times, we know it's true that they are much further apart than those in a solid or a liquid. Particles in a gas do move randomly, and compared to liquids and solids, they are at a high speed. That is true. And it is also true that the reason that particles in a solid are not moving around, it's not that it doesn't say that they're not moving, it says they're not moving around, because we've got to remember we describe the motion of particles in a solid as being vibrating about a fixed point. So you must have both of those parts in any description of the movement of particles in a solid. But here, they're not moving around, and the reason is because the forces of attraction between them, the stickiness, if you like, is very strong. So that concludes the second video on this topic. There were two more to go, but if you have any questions, let me know.